Hello all, my name is Anirudh Sikdar. I am a PhD student at the Indian Institute of Science, Bangalore, and I am about to present my work, Fully Complex Value Deep Learning Model for Visual Perception. Complex value deep learning is used in applications such as speech processing, robotics, and signal processing, mainly because they have complex value data. Complex value deep learning models have certain advantages compared to their real valued counterparts, such as richer representation ability, easier optimization, and superior MRI and SAR image reconstructions. Complex value deep learning models can also be used for image classification tasks, mainly because of the rich representation ability in the complex domain. The general trend as to training the state-of-the-art models is shown in the following block diagram. The labels and the labels are real valued, and the input image is also real valued. They are fed to the complex valued models. All the models operate only partly in the complex domain, and the image predictions are made using the real valued fully connected layers. Finally, the whole model is trained in an end-to-end manner using the cross entropy loss function. As shown in the training scheme, all the features are projected from the complex domain to the real domain within the model itself. And the final image predictions are real valued. This learning process is not optimal as it causes a loss of phase information. The rich representation ability of fully complex valued layers is not utilized in these training schemes, and most of these models operate only in the first quadrant of the complex domain due to the use of CReLU. Operating in the whole complex domain may improve the generalization ability of the models. Hence, we propose a novel fully complex valued learning to train a fully complex valued convolutional neural network, FCCNN. FCCNN has the same number of parameters as its real valued counterparts and is trained completely in the complex domain without the need to project it in the real domain to make image predictions. We also propose a complex valued loss function and a two-step training strategy for efficient training, for efficient learning and better convergence. The brief prerequisites of complex valued deep learning are complex valued convolution operation. Complex valued operation is defined as an operation between a complex valued kernel W and a complex valued input H and is given by the equation shown. Complex valued activation functions need to be compatible, need to follow Richtinger calculus to be compatible with complex valued backpropagation. Mainly, CReLU and complex cardioid activation functions are used as they are the extension of ReLU in the complex domain. The equation of the complex cardioid is shown. As seen in the figure, the cardioid activation function operates in the whole quadrant and is not restricted to the first quadrant of the complex plane. FCCNN is a shallow, fully complex valued network based on the CFARNet model. As shown in the table, it has 3 convolution layers followed by the cardioid activation function. Finally, image predictions are made using fully complex valued linear layers, and these image predictions are complex valued in nature. To compare these complex valued predictions with labels, we use a complex valued one-hot encoding of the labels. The on values of this encoding is 1 plus I and the off values is -1 minus I. We also propose a regularized complex valued hinge loss. A complex valued hinge loss is given as an equation shown, where y is the complex valued one-hot encoding and y hat is the complex valued predictions. For regularization effect, we mainly define two terms to update the error for correctly classified samples. The error threshold is given by the equation shown, which is e to the power minus 0.05 into epochs. This means that as the training progresses further with an increase in epochs, the e threshold decreases exponentially. Maximum threshold is defined as EM, which is the maximum of an absolute of the complex valued hinge loss between the predictions and the complex valued one-hot encoding of the labels. EM returns the maximum value from the samples of the batch during training. Finally, we use the following condition where E is set to 0 when the maximum error is less than the threshold and is set as it is in the otherwise. For misclassified samples, complex valued hinge loss remains as it is. Finally, we define E, which is shown in the equation, which is E Hermitian into E divided by 2n, where n is the number of samples. E defined here is a real valued loss function, as real valued loss function are used for complex valued backpropagation. Finally, the block diagram shows the fully complex valued learning scheme. To train the model, we have two training strategies, training step 1 and training step 2. The input is fed to the complex valued model FCCNN, where after the fully complex valued layers, the model is flattened and passed to the complex valued fully connected layers. The whole model is trained in an end-to-end manner using the regularized complex valued hinge laws. At the end of training step 1, the flattened vectors are stored. For training step 2, these flattened vectors are passed again through the complex valued fully connected layers. And this in the training step 2, the fully connected complex valued layers are trained again for the same number of epochs as a fine-tuning step. Orthogonal distributed theory states that the output of a complex valued fully connected layer has two hypersurfaces, real and imaginary. Either of these hypersurface is sufficient to classify the on and off values. This theory helps us to train the model completely in the complex domain, and in the training scheme, the network operates completely in the complex domain without the need to project it in the real domain. To validate our experiments, we compare the models on CIFAR 10, CIFAR 100, and SVHN. We compare FCCNN with state-of-the-art models such as DCN, Surreal, and CDS I and E. The models are trained on RGB data, lab encoding, and sliding encodings. These encodings are used to convert the RGB, 3-channel RGB image to 2-valued complex valued channels. We ask certain fundamental questions such as, is retaining phase information and operating in the complete complex domain and training completely in the complex domain yield in an improvement in performance? As shown in the table, FCCNN outperforms real valued CNN and DCN consistently on all datasets for all encodings. FCCNN attains comparable performance to the best performing CDS model on CIFAR 10 and SVHN. For CIFAR 100, it achieves the state-of-the-art performance with 25% less parameters. We try to justify the intuition empirically that training completely in the complex domain is more useful rather than training only partly in the complex domain. We also ask the question that does an extension of real valued CNN to the complex domain improve the performance? As shown in the table, extending the real valued CNN to the complex domain yields in a 1.25% bump. Further, using the fine-tuning step, it yields in a 2.65% bump on the large dataset. FCCNN has the least number of flops compared to DCN and all the other complex valued models. Finally, we analyze the performance of FCCNN on CIFAR 100. We show that the model trains within 15K iterations compared to other models. Hence, it generalizes better on larger datasets. Finally, for conclusions, we propose a novel fully complex valued FCCNN. We try to empirically justify that training completely in the complex domain and not operating only in one quadrant, but rather using all the quadrants in the complex domain yields an increase in performance. Extending real valued CNN to the complex domain consistently gives us a 2 to 8% improvement in performance. Using the regularized hinge loss and training strategy, this performance is increased by 2.65 for larger datasets. Hence, we show that fully complex valued training scheme can be used to train complex valued models for larger datasets as it helps it to generalize better. Thank you.